We will now start to look at the model definition that we are going to use for supervised learning. So that's the step 2. It's file 2 in the tutorial. And as I said, I'm just going to go through the tutorial and try to explain it in our view, because this is a very well done tutorial. So what you can do is in this tutorial you can have 3 model definitions. So there's a linear model, there's a multi-layer perceptron, and there's a convolutional neural network. I will try to explain basically just the most important one, which is the convolutional neural network. If you want to study the first model that you can use, if you want to try to compare the result on this street view house number dataset, you can run the linear regression model, which is given by this. You're basically learning a weight matrix W. If you want to do this, this is the code for it. A slightly more complicated model, this is just a linear combination of inputs basically, is if you want to have a combination of input and you want to have a sigmoid, and then you have a linear layer on top. So you have basically linear layer, hyperbolic tangent sigmoid, and then you do another linear layer. So this is what you can do in the second part of the model. The more interesting model for us is the convolutional network, which is basically a particular form of multi-layer perceptron, which is designed to get the input layer convolved by a bunch of features, like 4 for example, then subsample them, then do another step of convolution in another 6 maps, have 6 features, and then a fully connected multi-layer perceptron. And we've seen this in the previous lecture, number 4. All of these things are basically things that we've seen. The typical convolutional neural network has basically 3 modules. There's a filter bank. The input is a 3D array with n1 2D features map of size n2 by n3, for example. And you have certain components. So the output is also 3D array. It's composed of M1 feature maps of size M2 by M3. Usually it's about the same size. This is the mathematical operation that you do, and this is the 2D discrete convolution operation, and there's a hidden bias if you want to. It's like the model is like if each feature was detecting a particular feature of every location of the input. And it's like translating the input of a features detector. We'll translate the output, but leave it otherwise unchanged. Meaning you're operating with the same convolutional kernel all over the image. Use a nonlinearity, which is a pointwise hyperbolic tangent. In recent implementation from Jan LeCun lab has shown more sophisticated nonlinearities. For example, there's the absolute value of the hyperbolic tangent has shown to give good results in some features. Then there's the feature pooling or subsampling. It's quite an interesting part also on the convolutional network. This layer basically treats each map separately and computes the average value over a neighborhood. In recent work, there are shown that more selective pooling, for example, an L2 norm or L infinity norm, also known as max pooling, have shown to give very good results. So if you run LP pooling with these 2 values, you're supposed to get a pretty good result. In particular with the p equal 2, especially for smaller network, is very effective. With this way, you reduce the resolution of the output, as we said in lecture number 4, the previous lecture, and make it robust to small variation in location of the features, the previous layer. Traditional ConvNet use a pointwise hyperbolic tangent, but less recent models do not. Some ConvNets even don't really use this pooling layer completely, but just use strides larger than 1 in the filter bank to reduce the resolution. So you can save some computation that way if needed, but really downsampling always gives you an advantage because you reduce the size and you sort of make some kind of a form of a pyramid embedded into the deep network. So it's a very good step to do. So here is the convolutional neural network code that was given in this tutorial. It's very nicely written because he has a number of states, the first layer, second layer, output layer, third layer. There's a fan-in to try to figure out how many features are used at each layer and combination. Filter size is 5 by 5. Average pooling is 2, and there's a norm kernel that is used. So if you look at there's basically 3 stages. First 2 stages are practically identical, and then there's a 2-layer neural network similar to multi-layer perceptron that we've seen upstairs. So the first layer is a spatial convolution. The interesting feature to notice here is that they use, Clement Farabet decided to use random tables to connect the input features, so end state of 1, with a specific fan-in and with the output of number of features. So in this case you have number of features of 16 and you have a fan-in of 1. So you take one value from the free RGB or YUV, you take one of these and you convolve it by the 16 filters. Then you do an hyperbolic tangent. You do spatial LP pooling with the L2 norm with the pool size of 2. And then you do a subtracting normalization to basically subtract the 0 mean. You repeat exactly the same thing in here, and then you have a standard 2-layer perceptron. Some comments about this model are that the input has 3 feature maps, each are 32 by 32. And DNN spatial layers work on 3D arrays, so they basically convolve input with all the features that are needed, so you can do it in a single step. First layer applies 16 filters to the input map, each one 5 by 5. And produces basically 16 28 by 28 because it's eating a little bit of size. After L2 pooling, you basically get 16 14 by 14 because you divide 28 by 2. You have a pool region of 2 by 2, and then this is the output of the first layer. The second layer basically takes the 16 dimensions and then basically picks up 4. There's a fan-in of 4, so 4 of these 16 convolves them with a 5 by 5 kernel and creates 4 by 256 by 5 by 5 trainable kernel weights. And at the output you're gonna have 256 by 5 by 5 final stage after subsampling. You basically do 14 by 14, you lose 2 on each side, you get 10, and then you subsample by 2, so you get to 5 by 5. You then flatten all the 16 400 dimensional vector and you send it to a multi-layer perceptron. The L2 norm is used, recent work by Jan LeCun, because it's been shown to give slightly better results on smaller network than the harsher max pooling. And it's also not a great idea to have fully connected layers in internal layers, because you want to try to break the symmetry and make sure that some layers in the middle of the convolutional neural network can be alive or can extract the important features even though they don't have to rely on all the features that are extracted.